Hi everyone, I'm Teeratham Vitchutripop. I am a member of the 2023 risk cohort, and this summer I worked in the robot perceiving and doing lab where I was mentored by Jenny Wang and advised by Professor David Held. Today I'll be presenting my work titled TaskSeg, which is short for task-specific object segmentation through demonstrations. So a problem that we're trying to tackle with this project is that recent vision-based manipulation policies that reason about the geometries of objects require an accurate segmentation of the objects involved in the manipulation task. And it's an expensive process to obtain ground truth segmentations manually, especially when trying to adapt a policy to a wide range of different tasks. So segmentation itself is a relatively large field. And in this project specifically, we focus on semantic segmentation, which is classifying pixels into semantic classes. An architecture that does that, for example, is DeepLab v3. But one thing which constrains these architectures like DeepLab v3 is that they are limited to a certain number of classes, which is why newer architectures include language conditioning like LSEG does. Recently, there has been a lot of attention given to Segment Anything, which is trained on 11 million images and produces remarkable zero-shot performance with very accurate mean IOU performance in terms of segmentations. But the problem with Segment Anything is that on its own, it has no knowledge of semantic classes. Another work that we were inspired by is Moves, which uses videos to understand held object and hand object contact, and uses optical flow to generate pseudolabels, which are then used to train a model. And so our takeaway from that paper was that training on large amounts of imperfect pseudolabels can still result in good model performance. The large category of manipulation tasks can be classified or formulated into a relative placement task, which is a task where we have an action object which is moved to a pose and position relative to another object named the anchor object. And something we can assume is that within a demonstration of a relative placement task, the action object is going to be the object that experiences the most motion throughout a task demonstration. And we can see that for this specific task, for example, where the robot is going to insert a square disk onto a peg. Our solution to this is TaskSeg, which is an architecture that utilizes optical flow on video demonstrations in order to generate pseudo ground truth masks that are then used as training data to train a semantic segmentation model. So TaskSeg's architecture has two main stages. One is the generation stage, where we're generating pseudo ground truth training data to train our segmentation model using video demonstrations. And the second stage is actually training the segmentation model with the pseudo ground truth data. So for our pseudo ground truth generation, we have 5 main steps. So we first sample a demonstration from RL Bench, which is the simulated environment that we're working in. We then feed the first observation of the demonstration into a robot segmentation model that we trained with ground truth robot segmentations in order to get a mask of the robot. We then perform optical flow between the first and all the other observations within the demonstration. We aggregate the results, and we threshold in order to get the final mask. To aggregate the optical flow results within a demonstration, our method uses the following formulation. We get the optical flow between the first frame and all other frames in the demonstration. For each optical flow prediction, we calculate the magnitude for each pixel, perform an element-wise multiplication with the robot segmentation max in order to exclude the robot, and max normalize the robot excluded magnitude. We then sum this value together across all optical flow predictions, average it by the number of flow predictions, and threshold it in order to get the final mask. We explore 3 other aggregation methods as well. Method 2 adds a noise reduction step where we threshold each of the magnitudes to generate a binary mask we erode and dilate and apply to the magnitude. What's also different here is that we don't perform max normalization for each of the magnitudes, but instead we get rid of the averaging step and max normalize the summed magnitudes. Method 3 is similar to our chosen methods, only adding the noise reduction step method 2 introduces. Method 4 does not perform any aggregation, instead relying on a single optical flow prediction between the first and last observation. We conducted experiments to test the performance of training a segmentation model using pseudo-ground truth masks collected from video demonstrations. Specifically, we used DeepLab v3 as our segmentation model backbone. To train TaskSeg, for each task, we used 500 video demonstrations to generate a dataset of 500 pseudo-ground truth masks of the action object that can then be used to train the DeepLab v3 model. We compare our method to a DeepLab v3 model that is trained directly on the ground truth segmentation of the action object with the same number of data entries. We evaluated the performance of both models on an unseen test set of 50 images and compared their predictions to the ground truth mask, and this table shows our results. As you can see, our method is within the range of a 5% difference in MIOU with the ground truth model for the phone on base task and the shape sorter moon task. We do observe noticeably worse performance on the insert onto square peg task. And if we take a look qualitatively at the segmentations, we can see that our pseudo ground truth model actually gets at least a good ballpark of where the mask should be, but fails in segmenting out the hole in the middle of the square disk. We also see here in another comparison for the shape sorter task that our pseudo ground truth model produces segmentations that are qualitatively comparable to those produced by the ground truth model. So our takeaways from this experiment is that TaskSeg is able to produce segmentation masks that are within the range of 5% IOU difference with a model trained on the ground truth. And we're able to segment both large objects, like the phone in the phone on base task, and small objects as well, such as the moon in the shape sorter task. We produce imperfect but reasonable masks for more difficult object geometries, such as the square in the square onto peg mask, where we were able to generate a mask of the square, but not exclude the hole in the middle of the square. And the reason for that error is likely due to the optical flow. Additionally, we perform an ablation study comparing the flow aggregation methods mentioned earlier. For each method, we generate a data set of 500 pseudo ground truth masks from video demonstrations for each task using the compared methods. In cases where the generated mask turns out empty, we record the occurrence, ignore the mask, and resample a new demonstration until we get a data set of a total of 500 non-empty ground truth masks. To evaluate the quality of the mask, we directly compare the generated mask with the ground truth and calculate the IOU. We also calculate the percentage of masks that have an IOU below 0.6, as we have found through observation that, in general, masks with an IOU below 0.6 are low quality, the incorrect object, and/or include irrelevant objects. Our results can be found in this table. So as you can see here, our method produces the highest mean intersection over union. Method 2 produces the lowest empty mask rate, and our method produces the lowest percentage of masks that have an IOU below 0.6. And this is for the insert onto square peg task. And we can see a similar trend as well with the shape sorter moon task. So our takeaways from this ablation study are that our method produces masks that have the highest mean intersection over union, but also has the highest empty mask rate, meaning it has high precision but low recall. Method 2 produces the least empty masks, but its IOU is somewhere in the middle. Method 3 and 4 produce masks with the lowest MIOU and also has the highest percentage of masks that have an IOU below 0.6. Method 4 specifically consistently has the highest percentage of masks that have an IOU below 0.6, which further motivates our need for flow aggregation, as method 4 only uses single optical flow prediction between the first and last observation. In conclusion, we proposed TaskSeg, an unsupervised architecture that utilizes optical flow on video demonstrations to generate masks used to train a segmentation model, requiring no human manual annotation at all. Our experiments show that TaskSeg performs on par with a model trained directly on ground truth data, and our ablation studies motivate and provide insight into optical flow aggregation. Our future work focuses on incorporating language conditioning into segmentation in order to have a single segmentation model that takes in a description of the task and an observation of the scene and segments the action object accordingly. We'd love to expand to more novel objects and tasks, and you can see some of them here from RL Bench. And we'd love to test as well on real-world demonstrations, as we've only tested on simulated video demonstrations. Something that we also have to test is the segmentation performance and how it affects the downstream policy. And we'd also love to be able to segment long horizon tasks that involved multiple relative placement tasks. I'd like to thank Rachel Burchin, Dr. John Dolan, the RISC program, and its sponsors for making this project possible. Special thanks to my mentors at the RPAD Lab, Dr. David Held and Jenny Wang, and also other members of the RPAD Lab for their guidance and support on this project. Thank you for listening.